photons, what energy are you getting when you multiply?
I got 159.6 kilojoules per mole.
159.6
kilojoules per mole.
Okay, you did it in kilojoules per mole. Okay, yeah, this is okay. You put it in kilograms per mole. I mean in kilojoules per mole. They want this is supposed to be that. Calculate the energy in joules. It's okay, but this is supposed to be the notations you used here. The units are okay, but here if you look at this conversion that you are doing here, because we're just saying, if you are getting what I'm saying, you're okay with me saying 1 mole contains this number of photons, right? The Avogadro's constant, isn't it? Then the previous energy that we got was for 1 photon. So if 1 photon contains this number of this energy here, what will be the joules? What will be the energy for this number of photons? So your units can actually just be joules, like the way they asked them to be. They are saying calculate the energy in joules. So I would have just left it in joules or just kilojoules. No need of putting per mole, but it's okay. It makes sense. It means you understand. This, what you did is just write what I've written here. You're just telling us, say, in every single mole, there are these kilojoules of what? Of energy that are needed. Yeah, so your answer is correct. It's okay. This is okay.
Then for number 5, I thought to find what Rayleigh equation is, so I thought to answer it.
Okay, so in question number 5, so you're okay with these equations. Let me just give you a summary for the equations. This is V, this is C over this. Then you also know the second equation to say energy is equal to Planck's constant times the frequency. You know to say pali V tingafakepo C over lambda. We can modify this, right?
Yes.
This creates the third equation. Now there is this equation again that you learn to say energy in a quantum number or in an energy level shell is this guy. If I remember this guy right, some people put Z on top, but it's just okay. There's that change in energy formula that you calculate to say if you're having a transition from one energy level to another, you have this guy 78 times 10 to the power is negative 8 joules, multiplying 1 over the initial squared minus this is the final squared. You know, you've seen something like this before, right?
Yes.
So now the Rayleigh equation is just 1 over lambda is equal to the Rayleigh constant. Then we put 1 over this guy initial, then minus 1 over this guy final squared, something like this. This is the equation. You have never seen something like this before?
No. Okay. My physics lecturer, he doesn't write on the board, he just moves slides. So maybe when I was doing, I didn't.
Oh, you didn't take note. Okay. Okay, yeah, but this is then you hate videos, eh?
How do you say that?
Because you've never watched any of my videos that I've sent you before. I'm able to tell if someone has watched or not.
No, you only sent me 2 videos and I watched them.
Oh no, now like on the channel there are also other videos, like this is already there. I have taught atomic structure, all the parts you need actually.
Okay, your channel on YouTube?
Yes, the same guy I sent you the links on. Okay, so the Rayleigh constant here is this. So from there they were specific. The only tricky thing about this question is that they are saying use the Rayleigh equation, which is this guy here, to calculate the wavelength in nanometers. You know to say there's a conversion to say 1 meter is equal to 10 to the power 9 nanometers. Some people say 10 to the power negative 9 meters is equal to 1 nanometer. However you do it, the answer will still be the same, but this one is better because it's easy to remember, because a meter is big. You need about 10 to the power 9 nanometers to make a meter. So now we're looking for the wavelength. That's what we're looking for. But then the tricky thing is in the guys they've in the numbers they've given us. So they've already stated in the question to say N2, which is let me use the ones, the notations here. So here is supposed to be N1. According to the formula, If you're using zoomed, here they put a 1, here they put a 2. 1 just means where we are coming from. Then 2 just means where we are going. So they've given the question there. So 1 over lambda, you put your Rayleigh constant here, 10 to the power negative 7 per meter. 1 over, the initial there is 3, so 3 squared minus 1 over 6 squared. Then here you solve it like this. This will be 1 over lambda is equal to, when you multiply everything this side, you get your answer. Then now you cross multiply, because you're looking for lambda, not 1 over lambda. Then you get your answer. And the answer you're going to get is in meters. You multiply it by 10 to the power 9, it will be converted to nanometers. So when you multiply this here, let's do it together. So what is 1.097 times 10 to the power negative 7? Then here we're having 1 over 9 minus 1 over 36. What are you getting?
You said
1.097
10 to the power
negative 7.
Negative 7, then open bracket.
Open brackets, then you have 1 over 9 minus 1 over 36.
1 over 36. It's 0. Okay, please make on the number of zeros. Let me just try and make it.
Okay, so just yeah, but this is supposed to divide, but then let me just indicate for those guys who will be copying. So let's just say check. Yeah, then this, if this is your answer that you are getting, now you end up converting it to what you say. You say 10 to the power 9. 10 to the power 9 nanometers is the same as 1 meter. So that the meter and the meter cancels, we multiply this by that. So this is supposed to be something like a 1.9. Okay, this answer here, you may just punch this for me. Just punch 1, repunch it, 1 divided by, open brackets, 9.14, then times 10 to the power negative 8. Let's see what you get.
Okay. It's now become 10. It's still a long number, but it become 1094091.04.
109
4
4
0919
09
19
0.04.
Yes.
This is what you are getting. So now if I convert this to nanometers, say what we say, 1 meter is equal to 10 to the power 9 nanometers. So we can, okay, so be too big, but okay, 1.09 by 10 to the power 1, 2, 3, 4, 5, 6, 7. 7 plus that will be something like a 16 if I'm not mistaken. But okay, just for confirmation, you can check this at your convenient time, but I'll resolve it tonight, then I'll send the answers using my calculator. Okay, but this is what you needed to do on question number. So they're saying, what would be expected to see? Would we be expected to see the light corresponding to spectral line? Explain in brief. So the answer you should have gotten here, the correct answer is something like a 3 something if I'm certain, 340 something if I'm sure, in nanometers. So on the spectral line, it will be a color, should be, I think, red or orange. Yeah, in something in those lines. So, because you know the spectrum has those colors, RGB, right? So every color has its own wavelength. Yeah, so there are wavelength demarcations this side. Let me just forward it to you, yeah, on WhatsApp. So every color has its own demarcation, and once you're done doing your calculation, you can tell the region that you're dealing with. So you see the guy, I think, a minute from now on your Yeah, on your WhatsApp. So whenever we do calculations on the visible spectrum, we should be able to relate the wavelength with a certain color. So the answer, I think, should have been violet or something. Yeah, so there is always that. So that's what you need to do. But the steps are the same. So you just cross-check the Rayberg equation I've given you and try to redo it. You should get the same answer. Then the last question, did you manage to do the last question?
No, I just ended in number 4.
Okay, but on this one, you've seen the Rayberg equation, right?
Yes.
Okay, yeah. So let me just also confirm this guy here. The Rayberg equation as well. Okay, yeah, this is okay. Then, okay, here. Numez, I'm the one who made a mistake here. This has to be a 7. The constant, the Rayberg equation here, the constant is 7, not -7.
Oh.
Yeah, the constant. I'm just from checking it from the textbook. It's +7. So now if you punch it here, let's redo this part. If you punch it here at this point, what do you get?
Let me do it again.
Okay.
Then it was times 1 over.
You're getting?
Then it was times 1 over what?
It was times 1 over 9. You've opened brackets, right?
Yeah.
1 over 9 minus 1 over 36, then close brackets.
Okay. Now I now have 9 at 914 166.6667.
There's no point still.
The point is between the sixes.
Okay, 9141 66
point
6667
666.7.
then 7.
Yeah.
Okay, then now do the reciprocal of this guy.
Okay.
Yeah, this should work. Yeah, this is the answer that we got, I think. So now when you do the reciprocal of this,
now the answer is in a negative form.
yes, it has the power has to be negative.
Yes. It was 1.093
1.09
89 24.
Okay, times 10 to the power what?
-6.
-6.
Yes.
Okay, so this is what you are getting. This is a -6 meters. So now we want to convert this to nanometers. So we are multiplying it, multiplied by 10 to the power 9. So wavelength is equal to 1.0. It will be what? Should be something like
1093 point.
Yeah, 0.89, right? Something like that. This is okay.
Yes.
Yeah, this is the correct answer here, because this actually explained why we couldn't find it on the spectrum. Yeah, so when they say, can this thing be observed? No. So they're saying, would we be expected to see the light corresponding to spectral line explained in brief? So no, because the wavelength is off the limit of the wavelength that we have on the spectral line. Yeah, so this is not accommodated on the spectrum. Yeah, all the wavelength from the picture I've sent you, they have a limit to them, so this is not part. Yeah. So now let me show you the last one. The last one is on, they're saying, they're saying what? They're saying calculate the number of electrons that can be removed from metallic cesium when cesium is irradiated with red light of wavelength. So the wavelength has been given. So this is your question what? Your question number 6. So your wavelength is 700 nanometers. So we can convert this by multiplying by 1 meter is equal to 10 to the power 9 nanometers. So this is just going to be a 7.00 times 10 to the power negative 7 meters. I hope this is okay.
Yeah.
Then from here they're saying if the total energy used to remove it is this, so the energy was given to be in electron volts, that's 3.89 electron volts. They already told us to say 1 electron volt is equal to 1.6 by 10 to the power negative 19 joules. So we'll convert the energy in joules. So 1 electron volt is given to be 1.6 by 10 to the power negative 19 joules. So 3.89 electron volts will be how many joules? So that we can now have the electron volts cancelling out. So 3.89 times this guy here will give us what?
Okay. Um, 6.224 times 10 to the power negative 19. 6.224 times 10 to the power negative 19.
So this is the guy that we're getting. This is the energy that was needed. So now you need to know to say that equation you always use, say energy is equal to Planck's constant times this, or rather the one that you say this same equation. This is just for one thing when it's moving. Now if you want to find for so many things, you have to put the number in front. This is HV. You have seen this N I've put in front, okay? So energy for one photon or one electron is here. We don't put anything in front because it's just one thing. But if you know the number of the things that you have, you can always put it here, so that you multiply with the energy for one thing. You get the total energy for all those n things that you've been given. So now we're going to use this same equation, except there is n, then this is hc over that, because we are given wavelength, not frequency. So the energy, we found it, it's 6.224 times 10 to the power negative 19. We're looking for n, so let me just rewrite it this side, 6.224 times 10 to the power negative 19 joules. We're looking for n when you have 6.62, I think, is it 62, the Planck's constant?
Planck's constant is 6.626 times 10 to the power negative 24.
Then the wavelength is simply 7.00 times 10 to the power negative 7. Yeah, so here you need to put the joules seconds. Then here we need to put the meters per seconds, so that you see that the units will actually cancel out. So this is meters per seconds. Then down you just put this in meters. So now we're looking for n. So in short, n, I'll just solve it for you here, and you just have to punch it. So n will be 6.224 times 10 to the power negative 9 joules, multiplying 7.00 times 10 to the power negative 7 m, then divided by the down part is Planck's constant, 10 to the power negative 34 joules per second, multiplying the speed of light, which is just this guy here. So you can punch the top part and the down part. Be careful to put things in brackets the same way I've written them here. The joules and the joules will cancel, the meters and the meters will cancel, the seconds and the seconds will cancel. This will just give us particles, yeah, because we don't have anything. We're looking for the electrons. Actually, it's a name, so we'll use electrons. So what answer are you going to get?
I'm coming.
Okay. 2.19
036.
036.
Yes, but the numbers continue, but it was 1203.
Then is that times 10 to the power anything?
No.
Okay, so you get this guy. Okay. Yeah, so these are the number of electrons that were actually transferred. Is it how many can be removed from the number of electrons that was removed? So if you have the number of electrons, they could have actually continued the question and ask you for the mass. And you know, to say if you have the number of electrons, you can get the moles. The element is given there, it's cesium. So if you're looking for moles, you're looking for mass and you have the number of moles, you can just use the molar mass and the moles, then you get the mass. So they could have gone a step further and asked for mass. Yeah, so you just finish it off. Is this okay?
Yes.
So the formulas are key. We just say this came as a result of the energy that we always get is for one thing. When you say E is equal to H this, when you say V, or when you say energy is equal to H this over that, this is always for one thing that's moving. But if we know the number of those things moving, we can just put an N in front. So meaning we'll be getting the total energy of the any particles that we have. So now this question, they were asking for the number of electrons that were being transferred. So a group of electrons is what we sometimes call as photons. It's one and the same thing. Yeah, so if you're looking for this, meaning we're just changing it to be the subject of the formula. So that's how no wonder we made it the subject of the formula, and then that's what we are from getting. So this is basically the calculation part there. The rest, you just have to refer to your notes, or you can use Google. They will definitely not mark the definitions. They will focus on question 4 to 6. Yeah, so yeah. Is this okay?
Yes, it is.
Okay, so we can